In the last session, we defined algebraic extensions, and we found that a simple extension is always an algebraic extension. So the definition of, what do we call the definition of algebraic extension? An extension E of f is algebraic if every element of E is algebraic over f. And we have an immediate example. If alpha belongs to E is algebraic, then f of alpha is an algebraic extension of f. Now we want to extend this definition. The definition of symbol extension. We want to include more elements to f and make it a bigger extension of f, bigger algebraic extension of f. So let's start with another element. Let's say beta belongs to E. So we have several conditions here. E, F, and we are assuming that alpha is outside. Otherwise it is just an F which is of no interest to us. So alpha is outside F. So this is our f of alpha, and f of alpha is equal to the polynomials in alpha. P of x belongs to f of x such that the degree of P of x is less than, strictly less than, the degree of alpha over f. Meaning it is a polynomial, this contains the polynomials in alpha whose degree is less than the degree of alpha over f. Now we are going to extend this to include several elements from E. So we are going to take another different element B other than alpha. So this B can be here, let's call it as B0, or B can be inside f of alpha outside f, B1, or it can be outside f of alpha still inside E beta. If it is inside f, then the simple extension of f of beta 0 is same as f. If it's inside f of alpha, f of beta is equal to alpha. Because this is the definition of simple extension is the smallest extension containing, or actually it's contained in this. So the simple extension containing f of beta 1 is inside here. It will be somewhere here. It will be somewhere, something like this. So we are not actually looking for an extension bigger than f of alpha if you consider the second element to be inside f of alpha. So that is of no interest to us. We are trying to expand this to include more elements outside f of alpha. So let us assume that we are taking the elements from E but not inside f of alpha. Meaning f of alpha cannot be expressed as a linear combination of alphas. Sorry, beta cannot be expressed as a linear combination of alpha. So when you consider a field that contains f of alpha, beta and f, that will be something like this. It should contain both f of alpha and beta. So our objective is to find the smallest field containing alpha and beta and f. So we can reword this as to find the smallest field containing beta and f of alpha. And that is actually equal to the field, the simple extension of beta over f of alpha. And is denoted by f of alpha beta is equal to f of alpha beta. If the degree of alpha over f is equal to n, then f of alpha we can write it as a0 plus a1 alpha plus dash dash a n minus 1 alpha to the power of n minus 1 a belongs to f. Or you can say f alpha is generated by 1 alpha n minus 1. So we need to find out, we need to define this, we need to find out the elements, what kind of elements are there in this f alpha and beta. Either we find which form it is or the base elements. We have a result here, f. In the last class, if E is an extension of f and k is a finite extension of E, then the degree of k over f is equal to the degree of k over E times the degree of E over f. the vector space K over F is spanned by the base elements of the form alpha I beta j, alpha to the power of I, beta to the power of j, where I is 0 less than or equal to I less than or equal to n minus 1, and 0 less than or equal to j less than or equal to m minus 1, where n and m are the degrees of k over e and e over f. That is, k over e is equal to n, e over f is equal to m. And this is actually generated by this vector space, or this extension is generated by the elements 1, alpha, dash dash alpha and minus 1. This is generated by 1, beta, dash dash beta m minus 1. If this is an extension generated by the these n elements, and this is an extension generated by these m elements, then k over f is generated by the products of the base elements of these two. So similarly here, the base elements of f alpha beta are exactly same thing, alpha to the power of I, beta to the power of j, 0 less than or equal to I less than or equal to n minus 1, 0 less than or equal to j less than or equal to m minus 1. Here we need to note something. These m and m, n is the degree, or the degree of alpha over f, and m is the degree of beta over f of alpha. Here, if beta is not in f of alpha, then m will become the degree of beta over f instead of f of alpha. In fact, we don't need to have this condition, because if beta is already in f of alpha, then this becomes f. So you don't need to say that. So m is actually, this is all right. M is the degree of this, and that is again equal to the degree of beta over alpha. All right, we'll do some examples. Let us do some examples here. We'll take two polynomials in Q of x, x square minus 2 x cube minus 2. This is a polynomial of degree 2. So it can have an up to 2 zeros, and here it will be 3 zeros. And you know this is actually root 2 and minus root 2. Here, one of the real root is, we will write it as cube root of 2. We have 2 more complex roots. We are not going to deal with that right now. So when I say cube root of 2, actually q is equal to 2, then we normally write it as x is equal to cube root of 2. There are 3 different roots for this, or zeros for p2 of x. I am only going to consider the real, there is one real root and there are 2 complex roots. But I am going to consider only the real roots here. So, in other words, R is the whole domain, the biggest field, and here it is my Q. If you expand this one to C, then the other two zeros will be included in that. I'm not going to do that. I'm only considering root 2 and cube root of 2. These are all inside R. So our objective is to find the degree of f root 2 comma cube root 2 over, actually you can write it as cube over cube, and the base elements of cube of root 2 comma cube root 2. So these are the objective. And what is actually Q of root 2? Q of root 2, you know, it is actually generated by a plus b root 2 a comma b in Q. Or you can say the base elements are 1 root. Or you can say the degree of Q root 2 over Q is equal to 2. There are 2 elements here. The first thing we need to find out is that, so this is our Q root 2. The first thing we need to find out is whether cube root of 2 is inside here. If cube root of 2 is inside here, then what will happen? Assume that cube root of 2 is in Q. What does that mean? This means that Q cube root of 2, right? Because if it's inside this, then this is the inequality. So that means q of root 2 over q is equal to q of root 2 over, or you can say, or instead of writing all this stuff, you can say the degree of cube root of 2 divides q root 2 q, right? The result goes, it is from this result, like if k is an extension of E, which is an extension of F, all finite extensions, then we already proved that k over F is equal to k over E times E over F. This implies actually k over E divides k over F, and E over F also divides k over F. This is a multiple of these two, so each of them divides this. So that is what this means. What is this? This is actually 3, because the irreducible polynomial for which this is a 0 is x cubed minus 3. So x cubed minus 2, x cubed minus 2. So the degree of this polynomial is 3. And what is the degree of this? 2. So that means 3 divides 2. 3 divides, which is a contradiction. This is a contradiction. This is a contradiction. Meaning, we cannot assume that this is inside here. So this is actually totally outside. When we assume that this is inside this, then we are getting a contradiction that 3 divides 2, which is impossible. So this is a totally different element, not even inside Q of root 2. So the base elements, of Q root 2 are 1 root 2. You can say base elements of Q root 2 over Q is equal to 1 comma root 2, and the base elements of cube root of 2 over Q root 2, to be safe, 1 comma cube root of 2. One comma cube root of 2, no, not just this. 1 comma cube root of 2 comma cube root of square. Because it should have 3 elements. This should have 3 elements. None of them can be expressed in terms of root 2. Actually, this is same as q. So, the base elements of cube root of 2 comma root 2 are 1 root 2 cube root of 2 cube root of 2 whole square root 2 times cube root of 2 then root 2 times cube root of 2 whole square. There will be 6 elements. You multiply each of them, each from here and this. So you'll get this. We can write it like this. 1, 2 to the power of half, 2 to the power of 1 by 3, 2 to the power of 2 by 3, 2 to the power of 2 by 1 by 6, 2 to the power of 1 by 3, 1, 2, 3, 4, 5, 6, yes. 1, 2, 3, 4, 5, 6. And the degree of cube root of 2 comma root 2 over q is 6. Let us do one more example. Let us find out the degree and the base elements of q of root 2 comma root 3. Here again we have an r here, we have q here, root 2, root 3. So this is our q root 2. We need to find out whether root 3 belongs to this or not. If root 3 belongs to q of root 2, if root 3 belongs to q of root 2, then root 2 plus root 3 also belongs to q of root 2. Because q root is always in q root and q root 3 you are assuming that it is in this. So sum is always in this. But the irreducible polynomial of root 2 plus root 3 over q what is the irreducible polynomial here? If you take alpha is equal to root 2 plus root 3, then if you want to find out the polynomial, the reducible polynomial, then you square here root, so this will be 2 plus 3 plus root 6, 2 root 6. Then again you take this element here, square minus 6, minus 6 is equal to 4 times 6, 24. So the polynomial, the irreducible polynomial will be minus 24. So we can say the degree of is 4. I'm not going to expand and trying to find out exact value of this, but definitely it is a degree of 4. But if root 3 belongs to this, that means Q root 2 is a finite extension of Q root 2 plus root 3, which is a finite extension of Q. Because it's already here. If you are assuming that root 3 is inside here, so root 2 plus root 3 is here. So the simple extension containing this will definitely be smaller than this. If you are assuming root 3 is inside here. And this means that Q root 2, the degree of Q root 2 over Q or degree of Q root 2 plus root 3 over Q divides Q root 2 over Q. This is actually 4 and this is actually 2 because the irreducible polynomial is x square minus 2. So 4 divides 2, which is a contradiction. That is because we are assuming that root 3 belongs to this. So that implies root 3 does not belong to Q of 4. Then now we have the solution. Q root 2 is generated by the base elements 1 and root 2. Q root 3 is generated by 1 and root 3. Okay? The only intersection of these two extensions is Q. So the Q of root 2 comma root 3 is generated by 1 root 2 root 3 root 6. It's actually products of elements from here and here. So the degree of Q root 2 root 3 over Q is equal to 4. So we know everything about root 3 and Q of root 3 and root 2. We'll do one more example. C is a field of complex numbers. And can be considered as a finite dimensional vector space over R of dimension 2. Because any element of C can be written as A plus BI. So what does that mean? That means the degree of C over R is equal to 2. Either it's taken as a vector space or an extension of this field. Now let us consider Let us consider a simple extension of an element a plus ib for a fixed a and b. Fixed a and b, okay? Fixed a and b. What is this? This is actually equal to a plus ib, a comma b belongs to R. I don't want to confuse with this a and b. This will be C plus D. C plus D. See, this is, I'm talking about fixed elements A and B. These are all any element from C and D. Why this is so? Because how do you find the irreducible polynomial of this? Alpha is equal to a plus ib, alpha minus a is equal to ib, alpha square minus 2 alpha, 2a alpha plus alpha square is equal to minus b square. So this is a polynomial in, so this is actually alpha square minus 2a alpha plus alpha square, this is actually a square plus b square. So the polynomial, the irreducible polynomial is x square minus 2ax plus a square plus b square. So it's of degree 2. If it's a degree of 2, then the simple extension containing a plus ib and r is of this form. Actually, this is going to be alpha d. Alpha is actually, okay, let's make it as ideal. So, what does that mean? That means r of a plus ib over r, the degree of this is equal to 2. But again, r of a plus ib is definitely an extension of R and is a subfield of C. What does this mean? This means that the degree of C over R is equal to the degree of C over A plus IB times the degree of A plus IB over R. This is 2 and this is also 2. So that means this has to be 1. So that implies C colon R of A plus IB is equal to 1. Whenever you say the degree of, whenever you say a degree of an extension over E over F is equal to 1, that means E is equal to F. Because there is only one element that generates this vector space, and that is the identity of F. So this implies that C is equal to, the complex number equal to, the complex number is equal to the simple extension. So these are two different, I'm coming with from two different approaches. This is the set of complex numbers, assuming a complex number is a vector space. And this is actually a simple extension of a fixed element from a complex number.